Okay, section 2.1. I'm going to break 2.1 into two portions. So 2.1 part 1 is on page 97, quadratic equations. And what a quadratic equation in one variable is an equation that can be written as follows, where these letters A, B, C are numbers, and A cannot be 0, because if A is 0, that will make this a linear equation. If A is 0, that would be bx plus c equals 0, and you notice the power now is 1. So A cannot equal 0, that's called a quadratic equation. Knowing the name is not as important as you recognizing that it's quadratic, because we're going to learn everything there is about a quadratic in this class. That's a must. And we have a zero product property. It says if A and B are algebraic expressions, if you take A times B and get it to be 0, then A would equal a 0 or B would equal a 0. That's why multiplication is so important. If I told you A and B are numbers, and I said A times B equal 10, you could say 1 times 10 is 10, that works. You could say 2 times 5 equal 10, that will work. You could say negative 1 times negative 10 is 10. You could say negative 2 times negative 5 is 10, that will work. You could also say 100 times 1 over 10 is 10, meaning 100 times 0.1 is also 10. 100 times 1 over 100 is 10. The point is, I could list an infinite amount of multiplications that give me a 10. Only 2 of those infinite have a 10 in them. But if I tell you I multiplied two numbers and got a 0, you could say it's 5 times 0. You could say it's negative 30 times 0. You could say it's 0 times 0. You could say it's 0 times 1/5. The deal is, if you multiply two numbers and get a 0, one of them must be a 0. And that's what makes this property so useful. So, when I look at page 114 in our book, I'm looking at solve the following equation. This is quadratic. Anytime I see a quadratic equation, I'm thinking, okay, well, how am I going to do this? I see that I have it on both sides of the equation. If I am to get everything on one side, 0 on the other side. So if I move the 3 to the right, that would become a negative 3x minus 18 equals 0. So this is the riddle. Tell me a number in which, if I square it, then I take negative 3 times that number, and I add those and subtract 18, I get a 0. That riddle is very hard to do. Well, instead, if I make this sum into product, the key is to have a 0 on one side, everything else on the other side. And I know how to do that by factoring. So we said 1 and 1. And closest factors of 18 are 6 and 3. If I want a negative 3, negative 6 plus 3. Do you see now that this right here matches this right here? What that says, then either x minus 6 will equal 0, or x plus 3 will equal 0. And if I solve this, x would be a 6, or x would be a negative 3. So, generally speaking, of course that's not always the case, a power of 2 can get you at most 2 solutions. You could get less than that, but in general that's what you get. If I look at number 4, same deal. I see a quadratic equation, right? So I solved quadratic. There's only one exception. I'll show you what that is. Anytime I see quadratic, I say, well, these are 3 things added or subtracted. I need to get a 0 on one side, everything else on the other side. And the goal out of this is for me to factor if I could. That is, change the addition and subtraction into multiplication to be able to use this property. Because if two terms multiply to give me 0, then I know either the first equals 0 or the second equals 0. Well, that's why factoring is so important. I'm going to take 3 and 2, 1 and 5, 5 and 3, subtract to get me 13. 15 minus 2, again, I'm assuming you're factoring on your own. I never taught you how to factor. So this is going to be 3x minus 1 and a 2x plus 5. That's how this will factor. That means 3x minus 1 will equal to 0, or the second factor, 2x plus 5 will equal to 0. This I don't need. I'm going to put right there just for your notes. That means if I move the 1 over, I'll get 3x to equal a 1, or x equal divide by 3, 1/3. Or move the 5 over, that means subtract 5 from both sides, divide by 2. And I'm adding an example. I'm going to call this problem 4 prime, meaning the same directions as number 4. Just an example. This is also quadratic. I noticed that because the power, one of the powers is a 2. So the way it works, no big secret. On most quadratics, I get 0 on one side, everything else on the other side, and I factor to use the zero product property. So if I get 2x squared, if I add 6x to both sides, that will be 5x. If I subtract 25 from both sides, I'll get a 0 on one side, everything else on the other side. And now if I look at the factors, 2 and 1, 5 and 5, I needed to subtract to get me a 5. 10 minus 5 is 5. That works. I need a positive 5, so I need a positive 10 and a negative 5. 2x minus 5 and an x plus 5. So either 2x minus 5 will equal a 0 right there, or x plus 5 will equal a 0. Add 5 to both sides. Divide by 2 both sides. Subtract 5 from both sides. So I will get either of those will work. Again, what that means, if I substitute 5 halves in for x, the left side and the right side would be equal. If I substitute a negative 5 in for x, the left side and the right side will equal. And if you need to see that, I could show you that in class, just ask. Now I'm going to go back to radicals slightly and talk about imaginary numbers. Imaginary numbers, or some books call them complex numbers, same thing. We define I to equal the square root of negative 1, and if I square both sides, and that's all I need. So anywhere I see specifically a square root with a negative underneath, I write an I. And that pretty much is it. A complex number normally looks like a plus bi. It's a good habit to write the part that doesn't have an I, which we call the real part, and the part with an I, which we call the imaginary part. So, if I look at the next set of problems, we want to simplify. So, if I look at this, before I even begin, I'm going to say this is the square root of negative 1 times 20. That is the square root of negative 1 times the square root of 20. And we have just agreed that the square root of negative 1 would be always an I. And isn't this 4 times 5? Doesn't the 4 clear the radical? and what's left underneath the radical. But it is a good habit to write the number first and the variable after. If I look at 300, I would write this as the square root of -1 times 300. And I'm going to write this as the square root of -1 times the square root of 300. And one more time, I recognize that this is simply my I. And if I look at 300, isn't that 3 times 100? Doesn't that clear the radical as 10? And I have a 3 left underneath the radical. And again, it's a good habit to write the number first, you should, and the I after. And now that I'm getting more comfortable with this, and this is an example, of course, and this is an example. There weren't enough problems in the book, so I'm adding to those. So the book assumes you've seen this and the reviewing. I'm trying to really add more examples because I know some of you haven't seen this in a while. So, if I take this problem now and I want to redo it, for example, if now that I know what I know, if I wanted to do this example, wouldn't you say, instead of doing this step, and this step, wouldn't you say, you know what, I see a negative underneath a radical, why don't I do this straight and save myself those 3 steps every time? And then I'll say this is 3 times 100. This clears the radical as a 10. There's a 3 left underneath the radical, and put the I. If you prefer to show those steps, you can. That's not a problem. So from this point on, that's how I'm going to do it. Meaning, I look at this problem, I say, well, this is negative square root of 12. Minus. Do you see this negative underneath the radical? All what I'm going to do, make sure the I is outside of the radical. So all what I do, and you have to do this first, is clear the negative from underneath the radical. And now I would work this the same way we worked section 1.3. This is 4 times 3. That clears the radical as a 2. And there's a radical 3 left underneath the radical. There's a radical 3 left under the radical. And this is a minus. You copy that down. And this is 36 times 2. 36 clears the radical as a 6, and I have a 2 underneath the radical. And don't forget just to add the I, and there it is. Last portion we need on this section is this square root property, and let me show you what it says. Square root property. This is a special quadratic. And this is what it says. It says, if A is positive and x squared equals A, then x will equal plus or minus the square root of A. Basically, you square root both sides, and every time you square root both sides, you pick a plus or minus radical A. And that's pretty much what the square root property says. Now, if I see a polynomial or quadratic, I get everything on one side 0 on the other side. If I see one of these equations, that's how I solve any of them. Unless you only see a perfect square and numbers. So in this case, they say, solve by using the square root property. If I look at this, it's true I can get the 33 on one side and factor, but do you notice there's only a square and a number? There's no x to the 1. If that's the case, this is very efficient to use and extremely useful. So if I isolate the square by itself, meaning add a 7 to both sides of the equation, 2x squared equal, if I add a 7, that's 40. Divide by 2 both sides. So the goal is to get a perfect square equaling a number. And I just did. I have a perfect square on one side, a number on the other side. Then I could square root both sides, and I'm not going to forget to say it's going to be plus or minus. And what's this? Isn't this 4 times 5? Doesn't that clear the radical as a 2? And the 5 remains under the radical? So this is a special quadratic. The only special quadratic that we don't move everything to one side, 0 to the other side, and proceed. Instead, we isolate the square by itself, and you'll see in the next half of this section why we do that. Here I have an example. I'm going to call this 6 prime, another example. I noticed that this is a perfect squared, so it looks like this, kind of, except there's that 4 standing in the way, so I would divide both sides by 4. Why is that? Because I want a square on one side, everything else on the other side. 36 divided by 4 is a 9. And if I square root both sides, I'm going to remember, every time I square root both sides, I pick a plus or minus. Oops. The square root of 9 is 3. And wouldn't you just move the 5 over and say x equal negative 5 plus or minus 3? What does that mean? If I take negative 5 plus 3, negative 5 plus 3 is a negative 2. Or if I take negative 5 minus 3, negative 5 minus 3 is a negative 8. Number 8, if I was solving this problem, I wouldn't use the square root property, but here they say use it. So wait a minute, but I need a perfect square root. Well, that's what they're telling you. If you factor this, this is x minus 5 into x minus 5. Basically, this is x minus 5 squared. And we don't assume you're going to see that by looking at it. The fact that they say use the square root property gives you a hint. And now that I have a square equaling a number, I square root both sides. X minus 5 will equal plus or minus. Isn't this 2 times 100? Isn't the 100 a perfect squared? And what's left underneath the radical? A 2. And all what you have to do is add 5 to both sides. And one more problem before I conclude the first half of this and finish this second half next time. So I'm working a bit slower since you did mention that you're having a lot of, you forgot a lot of stuff. So I noticed there's only a square and numbers. I would move the 175 to the other side. If I subtract 175 from both sides, negative 25 minus 175 is negative 200. If I divide by 12 both sides, I'll get x squared to equal negative. If I divide the top by 4, that's a 50. The bottom by 4, that's a 3. 12. And if I square root both sides, x will equal plus or minus. I see there's a negative underneath the radical. I get that out of the way by throwing an I out, and I separate those. Square root of 50 over square root of 3. And x will equal plus or minus. Now, square root of 50, isn't 50 25 times 2? So this clears the radical as a 5. Radical 2 over radical 3i. And I need to rationalize. If I multiply top and bottom by radical 3, I will get x to equal plus or minus 5. Radical 2 times radical 3 is radical 6. Radical 3 times radical 3 is a 3 and an I. So I'm going to stop here for this section, and I will complete this in the next video. Let me give you the homework. And there's your homework on page 114. think it was 114, right? Let me make sure. Yeah, it is on page 114. My mistake. I'm sorry. Do numbers 1 through 11 odd.